Yep, looks great.
Okay, so hi everyone. So I'm a third year PhD student in Vivian Rebecca's lab here in Paris. And so I'm studying the impacts of a high-fat diet on hippocampal area CA2 and social memory. So CA2 can really be seen as a hub receiving various afferents from the emotional, social, and cognitive centers of the brain. And this unique connectivity really makes it susceptible to being modulated by lots of environmental factors such as enrichment or stress, as we've seen in the previous talk. And one of these afferents that it receives comes from the paraventricular nucleus of the hypothalamus, which is actually known to regulate metabolism. So oxytocin has been shown to alter food intake, and studies have shown that obese individuals have actually have a reduction in their levels of plasma oxytocin. And diet-induced obese mice have been reported to have a lower level of hippocampal oxytocin receptor at the mRNA level. So as we know that oxytocin modulates CA2 activity, we wondered whether diet could be one of these environmental factors that also modulates CA2 activity. So alongside all these oxytocinergic alterations, obese patients also have like a higher risk of cognitive decline, and diet-induced obese mice have been reported to have big learning and memory deficits, some of which are actually hippocampal dependent, and one of which is social recognition memory. So our collaborators in Bordeaux and Alice, who's listening right now, have shown that after 12 weeks of a 45% high-fat diet, spanning the period of adolescence, these mice actually have big social memory impairments, as you can see here. So I'm not going to go over this test again, as we've already seen it twice. But basically, they explore the familiar and the novel mouse the same amount of time, which is seen as a sign of social memory impairments. So because the oxytocin neurons of the paraventricular nucleus are actually highly active during periods of social interaction, and that when you knock out the oxytocin receptor in hippocampal area CA2, this leads to social memory deficits in mice, we wondered whether in the high-fat diet-fed mice, there's an alteration in oxytocinergic signaling, and that this might explain their alterations in social memory. So I had two big questions during my PhD. The first one was to understand how a high-fat diet alters hippocampal area CA2 properties basally. And the second one was more specific about this oxytocinergic signaling in CA2 and whether it's altered in these high-fat diet mice. So I started by looking at basal excitability of CA2 pyramidal neurons. So although no action potential and thus population spike, which is what I recorded here through field recordings, can normally be elicited through stimulation of Schaefer collaterals in control mice, in the high-fat diet mice, this stimulation actually led to big population spikes, as you can see here, which meant that a lot of action potentials were being fired from the CA2 pyramidal neurons. I then measured postsynaptic potentials upon Schaefer collateral stimulation too, both through whole cell recordings and field recordings. And so both at the somatic and dendritic level, the postsynaptic potentials seem to be larger in the high-fat diet mice compared to control. So overall, it seemed like the high-fat diet mice had this global overexcitability of hippocampal area C2, and this could be due to multiple things. So I checked all these things individually. I first wondered whether in the high-fat diet mice, there may be decreased inhibitory transmission. So I studied this through whole cell patch lamp recording, blocking excitatory transmission. But this inhibitory transmission was actually the same between high-fat diet and controlled diet mice. I'm sparing you the details for the sake of time. I then went on to look at the CA2 pyramidal neuron intrinsic properties by whole cell patch clamp 2, but I didn't find one that could explain a difference that could explain the difference in hyperexcitability in between the high-fat diets and controlled diets fed mice. Lastly, I wondered whether this hyperexcitability could be due to stronger excitatory transmission onto hippocampal area CA2. And I studied this using whole cell patch clamp recordings, blocking inhibition with GABA A and GABA B blockers, and measuring the excitatory postsynaptic potentials elicited by Schaefer collateral stimulation. As you can see here in the high-fat diet mice, this stimulation led to much larger EPSPs compared to control, which seems to confirm this last hypothesis. So this increase in the EPSP amplitude was also reflected by a decrease in the paired pulse ratio, which seems to indicate indicates a presynaptic focus of this change. So all in all, it seemed like the high-fat diet had this increased excitatory drive onto hippocampal area CA2. And this increases CA2 activity, which can be kind of represented as this increased noise in the system, which perturbs efficient social memory encoding. And so we wanted to test out if this increased activity actually does lead to the social memory deficits. And Alice in Bordeaux actually answered this question. So she actually injected floxed inhibitory drugs bilaterally into CA2 mice, which are supposed to decrease CA2 pyramidal neuron activity after CNO injection. So CNO was injected IP right before social memory testing in these high-fat mice. And as you can see, with MTR control, the high-fat diet mice have these social memory impairments, as I've shown previously. But when CA2 pyramidal neuron activity was decreased, this social memory was actually rescued. So this really confirms our hypothesis, whereas the social memory impairments of the high-fat diet-fed mice is due to this enhanced activity of the CA2 pyramidal neurons. So I then went on to the second part of my PhD project, which was to study if oxytocinergic signaling in hippocampal area CA2 was altered in the high-fat diet-fed mice. And in order to study this, I first need to know what oxytocin does on CA2 pyramidal neurons. And this has been published previously by some people here actually today. And so we know that oxytocin increases dendritic complexity, especially at the basal level of CA2 pyramidal neurons. We also know that oxytocin leads to depolarization and bursting of CA2 pyramidal neurons and leads to a long-term increase of excitatory postsynaptic potential upon stimulation of Schaefer collaterals, as well as a decrease in inhibitory postsynaptic potential. And it also changes action potential properties. So I went and studied all of these one by one. So first, starting by the dendritic complexity in high-fat diet mice, what I did was to reconstruct the CA2 pyramidal neurons I patched, and then I did some Scholl analysis on them. So the Scholl analysis revealed that the pyramidal neurons were less complex in the high-fat diet-fed mice, as you can see here. And quantitatively, the number of branches, basally nodes and terminals, were smaller in the high-fat diet group compared to the control diet group, which seems to be in line with a reduction of the oxytocin receptor in these high-fat diet mice in CA2. So I then went on to look at the effects of oxytocin on depolarization and bursting of the cells. And I looked at many parameters such as delta VM, bursting onset, burst duration, firing rate during the burst, as well as interburst interval. But none of these parameters were actually different in between the two groups. Neither were the proportions to which the cells bursted or did not burst. I then went on to look at the long-term chemical, the chemical long-term potentiation that 5 minutes of oxytocin application induces in CA2 pyramidal neurons upon Schaefer collateral stimulation. As you can see here, this is the data in control. It leads to long-lasting potentiation of responses. But in the high-fat diet-fed group, actually, this was not the case. And this chemical long-term potentiation was much lower. So this is indicative of an impairment of the oxytocinergic system in CA2 in these high-fat mice. I then went on to look at if oxytocin affected inhibitory postsynaptic neurons differently in both groups. And I did this through whole cell patch clamp recordings, blocking the excitatory transmissions and holding the cells at +10 millivolts to isolate inhibitory postsynaptic currents. And as you can see here, oxytocin led to a reduction of iPSCs, but this was the same amount in both groups. So lastly, I went on to see what oxytocin did to action potential properties in both groups. And so I first looked at AP amplitude and rise time. As you can see, AP rise time is not affected by oxytocin, but AP amplitude is decreased in both conditions, although not statistically significantly in the high-fat diet group. I then went on to look at AP half-width and decay. And as you can see, oxytocin leads to a big decrease both in AP decay time constant, as well as in the AP half-width. This actually made me notice that in general, it seemed like the high-fat diet-fed mice, even under basal conditions, had a shorter action potential. And when I went back to look at all of the cells I had recorded from, this difference was statistically significant. So in the high-fat diet-fed mice, there was much shorter action potential. And as you might know, a shorter action potential is synonym with less calcium entry into the cell, as was already shown by Gregor and Jonas back in 2000. So this kind of rang a bell to our team because we recently discovered this novel plasticity in hippocampal area CA2, which is highly calcium dependent. So as you can see here, it can be blocked by including BAPTA inside the recording pipettes. This plasticity is endocannabinoid dependent. As you can see, it can be blocked also when you intubate the slices with an inverse agonist of the CD1 receptor. And most importantly, this plasticity can be induced by social interactions. So here, after multiple social interactions, this plasticity is occluded in slice. So our new hypothesis was that maybe in the high-fat diet-fed mice, because the AP duration is reduced, there may be less calcium entry, thus less endocannabinoid release, and an impairment of this endocannabinoid plasticity, which may also alter their social memory. But this plasticity is actually dependent upon CA2 pyramidal neuron firing, action potential firing. And as I've told you at the beginning of my PowerPoint, when you stimulate Schaefer collaterals onto CA2, you can't get action potential firing basally. So in order to obtain this plasticity, we need to make CA2 more hyperexcitable. So in the Loisy et al. Paper that was published in Neuron previously, what they did was to disinhibit CA2 via a delta opioid receptor agonist. But I showed that we could also obtain this plasticity via application of 5 minutes of oxytocin right before the induction protocol, as you can see here. So I then wondered whether this plasticity would be altered in the high-fat diet-fed mice. And as you can see, after 5 minutes of oxytocin application and an induction protocol that leads to this endocannabinoid-mediated plasticity, there's a very low percentage of plasticity in the high-fat diet mice compared to control diet mice, which seems to indicate that there's an impairment in this plasticity in this population. So as a conclusive slide, we know that the high-fat diet mice have this overexcitable area CA2, which perturbs their social memory, but they also have this impaired oxytocin-induced endocannabinoid plasticity, which may be due to both impaired oxytocinergic signaling in CA2, as well as due to their reduction of AP duration. So I'd like to thank all of you guys for your attention, and specifically Vijay and Rebecca for their great help.